So in this lecture, we are going to solve a couple of problems. The first problem we are going to do is to find the Thevenin and Norton equivalent of the circuit that you see on the screen. It has a dependent source. And the first thing we are going to do is we are going to find the effect across the load resistor from this circuit. That means we are going to find how much current is going through the load resistor, what is the voltage across the load resistor, and of course the power dissipated in the load resistor. And the reason we are going to do that is when we will find the Thevenin equivalent of this resistor, we're gonna put the load back um, to the terminals A and B for that Thevenin equivalent circuit. And then we are going to find the current, voltage, and power again across the load resistor to prove that from the load perspective, both the circuits, the original circuit and the Thevenin circuits, are going to be equivalent to each other. So the first thing, as I said, we should do is to find the effect across the load resistor. So to do that, it's a pretty straightforward circuit. What we can do is we can combine RL and R1 since they are in parallel, and then we will have only one loop, and we can easily do the loop analysis and calculate the current in this loop. Let's assume that after combining these two resistors, we have, and I'm not going to combine them. I'm not going to create another circuit after combining them. I just assume that they're combined, and they're, let's call, R equivalent. So the combination of this will be R equivalent. Of course, VR1 is going to appear across the equivalent resistance because VR1 is the same across R1 and R. So we will have a single loop, and then we're going to apply KVL. Assume that the loop current in that case, when you have R equivalent, that is R1 and RL are replaced by R equivalent. Assume that the loop current is I. So we are going to find what the value is, the loop current I is. Once we have I, we can find what is VR1, and VR1 is going to appear across the load resistor. So we can find the current in the load resistor using Ohm's law. And of course, we can easily find the power as well. So that's the plan. So let's go ahead and execute our plan. The first thing we are going to do is to find the equivalent resistance. So let's open MATLAB. We can do pretty much everything in MATLAB. Let's go ahead and plug in all the values. So I have Vs is 10, R1 is 170, R2 is 330, R3 is 200, and the load resistor is 220 ohms. And R equivalent will simply be R parallel of R load and R1. I'm using my parallel function in Octave. And that equivalent resistance is coming out to be 95.897 ohms. So this is, let me change the color of the marker. This is 95.8. We can call it 95.9, 95.897. Okay, so once we have this, I'm going to write down the KVL equation. So we have Vs minus Vd will be equal to I times R equivalent plus R2 plus R3. Remember, we replace R1 and RL by R equivalent, and we will have only a single loop. Okay, and Vd is half of VR1, and VR1 will simply be I times R equivalent because, again, the parallel combination is R equivalent. So Vs minus half of I times R equivalent is equal to I times R equivalent plus R2 plus R3. And from this, we can easily find out what is the value of the current I. And I will simply be Vs. Take this on the other side. That's going to be Vs plus, sorry. It's not minus because both the voltage source and the dependent source are in the same direction. So the voltages will be added together. So it is going to be Vs divided by, and this is going to go on the other side. It's going to become 0.5 R equivalent. So 0.5 R equivalent plus R2 plus R3. And that is going to give us I is equal to Vs divided by 0.5 times R equivalent plus R2 plus R3. So 0.0173 or 17.3 milliampere. So 17.3 milliampere, which implies our voltage across the load resistance and resistance R1, which is the same, is going to be I times R equivalent, which is VR1, we are calling it. So VR1 is equal to I times R equivalent, which is 1.6593 or 1.66. So 1.66 volt. And this will give us the load current. I load current is equal to VR1 over R load. And that is going to be IRL is equal to VR1 oh, VR1 divided by RL, 7.54 milliampere. So 7.54 milliampere. So that's my load current. My load voltage, of course, is VR1, 1.66 volt, and the load power is going to be, VR1 times IRL, or IRL squared times RL, whatever you want to call it. As long as you have the, in the Thevenin circuit, as long as you get the same voltage and same current, of course, the power is going to be the same. So these two quantities are important because in the Thevenin circuit, we are going to be looking at these two quantities and comparing from the Thevenin circuit to see if we get the same results or not. If we do, that means our Thevenin equivalent circuit is equivalent from the load perspective. Okay, to create the Thevenin circuit now, we can use either method 1 or we can use method 2. So you have to decide which one is going to be easier. Remember, in method 1, we are going to short circuit RL, or we're going to short circuit nodes A and B. Of course, RL is going to be removed. We're going to short circuit nodes A and B. Now, if we short circuit nodes A and B, that means R1 is going to be eliminated because no current is going to flow through the passive component R1, which means the short circuit, of course, will make VR1 to be equal to 0. And if VR1 is equal to 0, then VD is going to be equal to 0. And when a source voltage is 0, that means that source is basically shorted out. It's not producing any voltage, which leaves us to a very simple circuit. That is, you're going to have R2, Vs, short circuit here, and R3. And from that, we can find out the short circuit current. And then, of course, before that, we have to find out what is the open circuit voltage between nodes A and B. And the ratio between the open circuit voltage and the short circuit current is going to give us the value of Thevenin resistance, as we did in our last lecture. So let's go ahead and first, let's employ method. Okay, so let's also discuss method number 3. Method number 3 is that you short circuit all the independent sources, voltage sources, and open circuit all the independent current sources. Of course, there is no current source in this circuit. So in method number 3, we are going to short circuit Vs, and we are going to introduce a test source right over here between nodes A and B. So once you put a test source over here, of course, we will know what is the voltage at node A. That is, we will know what is VR1, which will be equal to the voltage of the test source. So we can know what is going to be VD, which will be half of the voltage of the test source. So again, the method is going to be very simple because we are trying to figure out what is the test source current. So you can easily, since you know the voltage at node A, you can easily find using Ohm's law what is the current passing through R1. And also you can find this current, which will be the test source voltage minus VD, which will be half of the voltage of test source, divided by R2 plus R3. So that current is also very easy to find out. And you can add both currents to find the test source current. So both methods are, I think, easy. In my opinion, the second method is the easiest because you will just have to find short circuit current using a single equation, and that's about it. So I encourage you to do this using the third method as well for practice. I'm going to do it with the second method only, and I'm going to leave the exercise, leave this problem as an exercise to use the third method of Thevenin equivalent to find the Thevenin equivalent resistance. So you can do that, and I'm going to go ahead and employ the second method only. So first, we're going to find out what is the open circuit voltage, that is, what is the Thevenin voltage. So Thevenin equivalent circuit using method number 2. So what we are going to do first is we have the voltage source, we have the resistance, we have the resistance here, we have the resistance here, and we are going to leave our nodes open, nodes A and B. So this is R1, VR1, VS, R2, R3, and VD, which is half of VR. Okay. So we are trying to find basically the open circuit voltage, which is the same voltage as VR1. So let's go ahead and simply do the loop analysis again. I1, let's call it I1, since we call I in the last exercise or last part. So let's call this I1 and write down the equation. So once again, Vs plus Vd equals I1, R1 plus R2 plus R3. And in this case, Vd is simply half of VR1. VR1 will be I times R1. So Vs plus half of I times R1 equals, or I1 times R1, I1 R1 plus R2 plus R3, which will give us the value of I1 from the equation, Vs over 0.5 R1 plus R2 plus R3. So let's find this out. I1 is Vs over 0.5 times R1 plus R2 plus R3. So 0.16260, so 16.26 milliampere. 16.26 milliampere. Which means that our open circuit voltage, which is equal to VR1 circuit, which is equal to Thevenin voltage, is I1 times R1, which is going to be equal to V open circuit is equal to I1 times R1, 2.7642 volt. Okay, so that's our Thevenin equivalent volt. And now, as we discussed, we have to find the Thevenin equivalent resistance. So method number 2 calls for shorting out A and B and find the short circuit current. So again, when we short A and B terminals, R1 is going to be eliminated. And since the voltage VR1 is going to become 0 because it's parallel to short circuit, then of course VD is going to have a 0 volt, which means we can short out VD as well. So we will only have VS, R2, and R3 in this loop, and of course short circuit. So R Thevenin, short terminals A and B, R1 will be eliminated, and VR1 will be equal to 0, which means VD is equal to 0, which implies VD will be short circuit. Anytime the source voltage is 0, basically you can replace it by a short circuit. Or you can just keep it and just show that it has 0 volt. It's going to give you the same result. So our final circuit, when we do this, is going to be R2 VS short circuit AB, and so this is A, B, and we are trying to find the short circuit current, ISC. This is my VS, R2, and R3. So the short circuit current, simply using Ohm's law, is VS over R2 plus R3. Zero 0.018868 or 18.86 milliampere. 18.86 milliampere. And from this, we can calculate the Thevenin equivalent resistance, which is the ratio between the open circuit voltage to the short circuit current. Open circuit voltage is the same as the Thevenin voltage. $146.50. 146.5 ohms. That's my Thevenin equivalent resistance. So this will result in a Thevenin circuit with Thevenin and R Thevenin. So this is our Thevenin circuit. So V Thevenin value is V open circuit. R Thevenin, of course, is 146.5 ohms. And V Thevenin value is V open circuit 2.7642 volt. 2.7642 volt. And across our node, we have our load connect. 220 ohms. Nodes A and B. All right, to prove the equivalency, remember, we have to find out what is the current that is flowing through the load resistance and what is the voltage across the load resistor. So very simple, it's a single loop circuit. IL is simply using Ohm's law. V Thevenin over R Thevenin plus RL. And once you have the load resistance, then of course the load voltage will simply be IL times RL. Let's calculate and see if they come out to be the same. So I load is equal to V open circuit, since with Thevenin is V open circuit, divided by RL plus R Thevenin, RTH, uppercase, RTH. And the value is coming out to be 7.5421, which is exactly the same as what we calculated from the original circuit, 7.5421 that you see here, 7.5421 milliampere. And since the value is same, of course, the voltage will be same as well. So VL is equal to IL times RL, 1.6593 volt, 1.66593. These two values are the same as 1.66 volt. I rounded that up, and 7.54 milliamp. So 1.66 and 7.54 milliamp. Same as calculated from the original circuit. And therefore, we can conclude that from the load perspective, the Thevenin circuit and the original circuit, they are equivalent to each other because the load is getting the same effect from the two circuits. So this is how you can prove basically Thevenin equivalent circuit, that the load is having the same effect or not. If you want to convert the circuit into Norton, very easy. You just apply the source transformation here, and Norton circuit will simply be you have the Norton source, the Norton resistance, which is the same thing as Thevenin resistance, and nodes A and B, across which you will have your load resistance connected. And the Norton source, IN, will be equal to V Thevenin over R Thevenin. So that is going to give you the Norton equivalent circuit. All right. The next item I want to do, solve another problem. And this time we are going to review the superposition method. Superposition method is employed on linear systems. Linear systems are the systems, actually they're defined by the superposition, that if the superposition can be applied on a system, then the system is considered to be a linear system. Superposition is what? Superposition is basically, as you know, pretty much all of you know, that if you have multiple sources in a circuit, and you want to find out the contribution because of each source, either it's the current passing through some part of the circuit or the power supplied to some component, you can find the contribution of each individual source by eliminating one by one each sources and keeping only one source alive in the circuit, and then solving the circuit because of that source. So you can find the contribution because of that source. And the total contribution, of course, is going to be the sum of all the contribution that you have found by eliminating each source one by one, or eliminating all sources and keeping one source alive in the circuit. Now, the only condition again for the superposition is that if you do have a dependent source in the circuit, that cannot be eliminated. So you only eliminate the independent sources. Dependent source stays in the circuit. So let's do a problem. So this is superposition. So a circuit with multiple independent sources can be broken down into multiple circuits, each with only a single source, independent source, and the effect due to only that source can be calculated for any component. The total effect will be the sum of all the individual effects by each source. So a voltage source, of course, if you're eliminating a voltage source from the circuit, it has to be open short circuit, and current sources will have to be open circuit. Now, again, we don't eliminate a dependent source. So dependent source stays in the circuit. So let's go ahead and solve perhaps a couple of problems. So problem number 2. Let's assume you have a simple circuit. And I'm just going to put 2 sources. Let's call it I2. Let's call it V1, R1, R2, and R3. V1 is 20 volt. I2 is 1 milliampere. R1 is 510 ohms. R3 is 770 ohms. And R2 is 680 ohms. And let's calculate. Determine the contribution of power supplied by each source to R3. So we want to see the power supplied to R3 by V1 and I2. What is the breakdown of that power? How much power is supplied by V1 and how much power is supplied by I2? So we are going to use superposition, eliminate each source one by one, and then find the power due to only V1 and due to only I2, and that will give us the individual contribution. And the total power, of course, is going to be the sum of both powers. So using superposition, keeping only V1 in the circuit. So when we keep V1 in the circuit and eliminating I2, that is open circuit I2, of course, open circuit I2. Of course, current source are made open circuit. So when we open circuit I2, of course, this whole branch is going to be gone, and we will have only one loop with V1, R1, and R3. V1, R1, and R3. And from that, we can calculate the current and we can calculate the power. Let's call this IR3 prime, IR3 prime. So IR3 prime will simply be V1 over R1 plus R3. And once we have IR3 prime, we can calculate the power. PR3 prime due to only V1 will be IR3 prime square times. Let's go ahead and calculate this. Let's go ahead and plug in the values. Here, CLC. Okay, so V1 is 20. I2 is 1 milliampere. And R1 is 510. R2 is 680. And R3 is 770. And we have IR3 prime. I'm just going to call it IR31 equals V1 divided by R1 plus R3 plus R3, 15.625 milliampere, 15.625 milliampere. And then the power is going to be PR3, let's call it PR31 equals IR31 square times R3 as 188 milliwatt. 188 milliwatt. That's the power contribution to R3 from V1. Now, eliminate V1 by short circuiting it. And calculate the power contribution from the current source. So we short circuit this R1, R3, R2, and the current source. I2, R2, R1, and R3. Okay. So we have to find again the power in R3. We're gonna call it PR3 double prime maybe. And let's go ahead and solve it. We can combine R1 and R3. They're in parallel to each other. Then the current in this loop will simply be I2, and we can calculate the voltage across R3. And once we have the voltage across R3, which will be the same voltage across R1 as well, then we can easily calculate the power that is dissipated in R3. So let's go ahead and do that. Let's combine these two. Let's call this R13 is equal to R1 parallel to R3. And that R13 is going to be R13 is equal to parallel between R1 and R3, 306.80, 306.8 ohms. So the current I2 is going to be flowing through R2 and R13 because it's just going to be a single loop, and the current in the loop is I2. Therefore, we can calculate the voltage drop across R13. So VR13 will be equal to I2 times R13. VR13 is equal to I2 times R13. 0.3068 volt. 0.3068 volt. And that VR13, remember, is going to be the same across both R3 and R1 because they are parallel to each other. So we can easily find. Therefore, power in power dissipated in R3 due to I2 is going to be, we can use V square over R, P R3 double prime is VR13 square over R3 because the voltage across R3 is going to be VR13 and across R1 is going to be the same. So power in R3 due to source 2 is equal to VR13 square divided by R3. Oh, very small power. 0.122 milliwatt or 122.24 microwatt. 122.24 microwatt. So this is a contribution of power from the current source. And of course, earlier we found the contribution of power from the voltage source. And the total power, of course, that is dissipated in R3 is going to be the combination of both. So total power dissipated in R3 will be the combination of R1 P, not R1, sorry, is going to be PR3 prime plus PR3 double prime. Whatever the result is going to be, you can add. Okay, so that's a simple problem to show how you can carry out superposition on a circuit. Superposition is a linear rule. That is, if your sources are linear, that is, they're changing the slope of those sources, or you can apply Ohm's law basically. Ohm's law is a linear law. But on any linear circuit, you can apply superposition, and the contribution of the contribution due to each source, each independent source can be found out individually by eliminating the other sources, opening the current sources and shorting out the voltage sources. And one by one, we do that, and we find the contribution due to each source. And the total contribution will be the sum of all the contributions. Okay, the last problem that I want to do is I want to do superposition, but I also want to have an independent source. So that's going to be my problem number 3, which will be the last one for this lecture. Apply superposition to find the total, let's say current somewhere. So total current passing through, I'll just make a resistor 1. So let's do a circuit. Let's say you have, um, a dependent dependent current source. Let's take dependent current source, and you have a resistor here, and then you have a resistor here. You have a resistor here. Okay. And let's call this R1 resistor. And this is an independent current source, and this is an independent voltage source. R2, R3, R4, and this is my current IR. Let's say that this dependent source, so let's call this our V1 20 volt, I2 20 milliampere, R2 400 ohms, R3 910 ohms, R1 1 kilo ohm, and R4 2.2 kilo ohm. And our dependent current source, let's say it is a voltage dependent current source, and the voltage is the voltage across R3, VR3. So VD is, let's assume, half of VR3. Okay, so this is the problem. We apply superposition, but we cannot eliminate VD. So do not eliminate when applying superposition. So let's go ahead and eliminate only the independent sources. I'm just going to go ahead and eliminate V1 first. That's going to become a short circuit. So eliminating V1. So our circuit is going to be That is going to be our circuit. R2, R3, VR3, I2, R1, R4, and it should not be VD, sorry, it should be ID as the current source. So ID is half VR3, ID. So this is our circuit. And our goal is to find what is the current passing through IR1 due to I2. So let's go ahead and solve this circuit. Let's see what is the easiest way to solve this circuit. Of course, we know that the current in this loop is going to be ID. So that current is ID. We already know that. Well, we can apply, so we can apply a super mesh. Or we can apply nodal analysis. Both are going to give you two equations. Nodal analysis, basically we can apply it. We can take one node over here. We already know the value of I2. So we can take one node over here and we can take one node over here. And we can apply nodal analysis as well. Let's go ahead and apply nodal analysis and then see what we get. As I said, both are going to give us two equations. So let's say I have a node A over here and B over here. So KCL at node A. Let's apply some currents. IR1 is going there. Let's assume IR3 is coming. IR2, well, this is R3, I'm assuming, not R2. R3. Let's confirm. R2, R3, R1, R4. Yeah, that's R3. Okay. So IR3 is here. And let's call this IR2. Ground. So KCL at node A. Node A is this. ID is going towards, IR1 is going away, IR3 is going towards. So ID plus IR3 is equal to IR1. Okay, ID is half of VR3. IR3 is VB minus VA over R3. And IR1 is VA over R1. Okay, VR3 is simply VB minus VA. So ID we can write down in terms of VB minus VA. VB minus VA over R3 is equal to VA over R1. So we can write down one equation in terms of VA and VB. Let's write down VA first. So I'm gonna just take both of these on the other side of the equation and make VA positive. So VA will be equal to 1 over R1 and plus half and plus 1 over R3. And now VB are going to go on the other side of the equation and both are going to become negative. So negative VB 1 half and 1 over R3. And this is equal to 0. So that's my equation number 1 in terms of VA and VB. Okay. Equation 2 is going to be at node B. So KCL at node B. Let's see what the KCL equation is. So IR3 is going away from node B, I2 is going towards, and IR2 is going towards. So I2 plus IR2 is equal to IR3. I2 plus IR2 is equal to IR3. I2, of course, we know. IR2, let's see. Okay, IR2 is simply 0 minus VB, so negative VB over R2. Negative VB over R2. And IR3 is VB minus VA over R3. So from this equation, I have negative VA over R3 plus VB 1 over R2 plus 1 over R3 is equal to I2. So I took this VB over R2 on the other side of the equation. And that's my equation number. So we're going to go ahead and solve these two equations, and we're going to find out what is the value of each node voltage. And once we have the value of node voltage A, we can find out what is the value of the current IR1 due to I2. So let's go ahead and do that. I'm going to have to enter values in my MATLAB first. Clear. Okay. This page up a little bit. Oh, I did not assign values. Interesting. So let's go ahead and assign values. Let's say, no, I did assign value. Actually, this is the second circuit where I eliminated. This is the original circuit. Okay, so all the values have been assigned. Okay, so R4 is 2.2K, R1 is 1K, R3 is 910 ohms, R2 is 400 ohms, and I2 is 20 milliampere. And let's see. And let's see, R4, R1, R3, R2, I2, and V1. V1 is left. So V1 is 24. I believe these are all the values, right? R4, R1, R3, R2, I2, and V1. Okay. So let's go ahead and solve the linear equations that we have from equation number 1 and equation number 2. So my coefficient matrix is going to be from equation number 1 is 1 over R1 plus half plus 1 over R3, coefficients of A. Coefficients of B are negative half minus 1 over R3. And my second row is going to be from equation number 2, negative 1 over R3 for VA, negative 1 over R3, and for VB, 1 over R2 plus 1 over R3. So this is my coefficient matrix A. My constant vector C on the right-hand side, the first constant value from equation 1 is 0, and the second is I2. Therefore, my two voltages are going to be A backslash C, and my two voltages are 7.9771 and 7.9930, very close to each other, interesting. So these are my two voltages. Okay. So solving simultaneous linear equations. So this is my VA and this is my VB. VA and VB. Interesting. VB is higher, so our voltage across R3 is positive, just barely though. Okay, anyways, whatever the values are, doesn't really matter. So now, what was our goal? To find the contribution of to find IR1 due to each source and then add them together. So IR1 due to, therefore, IR1 due to the current source will be IR1 let's call this IR1 prime equals what was that? Is that VB or VA? That is VA over R1. So VA over R. IR1, I'll just call it IR11 is equal to VA over R1. Okay, VA is not defined. Oh, VA is basically V of 1. 7.977 milliampere. 7.977 milliampere. So that is the contribution due to the current source. Now, let's eliminate the current source, the independent current source. And find IR1 due to the independent voltage source. Okay, so let's see the circuit, how it's going to behave. So we remove the independent current source, that loop is going to be gone. I mean, that branch is going to be gone. It's going to be open circuit. And we're going to insert the voltage source back over here. Let's go to the actual circuit actually. So we're going to, we have the voltage source here. This will be eliminated. So this is going to be our one loop here. And of course, there's nothing changed over here. So let's go ahead and do that. So we have R2, R3, R1, R4, independent current source, and independent voltage source. This is R1, IR1. Let's call this IR1 prime. And double prime, and let's call this IR1 prime in this circuit. So R4, R3, R2, R4, R3, and R and B. Okay, so this is our circuit. Once again, the current in this loop is going to be ID, and the current here we can easily find out using mesh analysis. IR1 prime is going to be the difference with based on the direction, either the sum of the two loop currents or the difference between the two loop currents. Once again, the other thing that we can do is to apply nodal analysis over here. and find the node voltage and then find the current. And both are just going to give you one equation, doesn't really matter. Let's go ahead and just apply the mesh analysis. So you have the current ID, and then you have let's call this current I1. Okay. So all we have to do is to write the equation for I1. And then VR3, since ID is half of VR3, I believe this is VR3. This is VR3 right now. So VR3 simply is I1 times R3. So that's going to become half of I1 times R3. That's going to be ID. All right, so let's write down KVL in the loop with the independent source. And that is going to give us V1 is equal to I1 times R1 plus R2 plus R3. And then ID is going in the same direction. So plus ID times R1. So V1 is equal to ID, of course, is half of I1 R3. So I1 R1 R2 R3 plus ID is half of I1 R3 times R1. So it's all I1, so we can easily find the value of I1. I1 is equal to V1 V1 divided by R1 plus R2 plus R3 plus half of R3 R1, half of R3. Okay. Let's see what I1 is going to be. I1 is equal to V1 divided by R1 plus R2 plus R3 plus R1 plus R2 plus R3 plus half of R3 R1. 0.5 times R1 times R3. 4.37 exponent negative 5 or 43.73 microampere. 43.73 microampere. So since we have this I1, now the current IR1 prime is the sum of ID and I1. IR1 double prime is the sum of ID plus I1. Of course, ID is, what is ID? Half of VR3 or half of I1 times R3. Half of I1 times R3 plus I1. Because the current source is voltage dependent current source. So IR1 prime, double prime is going to be IR1, I'm going to call it 2, is equal to 0.5 times I1 times R3 plus I1. So 0.0199, so 19.94 milliampere. This is the contribution of the current that is flowing through R1 due to only the voltage source. Therefore, the total current the total current flowing through the resistance R1 is IR1 is equal to IR1 prime plus IR1 double prime, which will be equal to IR1 is equal to IR11 plus IR12, 0.02792, so 27.92 milliampere. 27.92 milliampere. And this is our final result that was required in this problem.